Okay, students, I just want to take a few minutes to offer this supplemental video. There isn't a section in your lecture workbook for these notes, so I'm just going to make them in the margin here of this section on noble gas shorthand configurations. And in a future version of this workbook, I will actually have a section for these notes. But there are two things that I want to talk about here that are relevant to what we've just covered in this noble gas shorthand configuration for electron configurations. And the first is a concept called the valence shell or the valence level. And I just want to make sure that we understand what that means. I mentioned it in our previous video, and I just want to confirm what we mean when we say valence, V-A-L-E-N-C-E. And valence just means the highest energy level. That is the highest N value or the highest shell that has electrons in it. So it is the highest energy level, which we know is the N value, the highest energy level with electrons in it. So let's take a look back at some of the work that we've done. If we look at barium, silicon, tantalum, bromine, oxygen, and lithium, we can readily see that the highest N level, the highest energy level that has electrons in it, the valence level for barium is the N equals 6. So a valence shell or valence level is always an N value. So the highest N value, the valence level for barium that has electrons in it is the N equals 6. For silicon, the valence level is N equals 3 because it is the highest N value that has electrons in it. For tantalum, the valence level is, what's the highest N value here? It's the 6 that has electrons in it. For bromine, the highest N value with electrons in it is 4. So the N equals 4 level is the valence level or the valence shell. And another way that we refer to the valence shell is the outermost shell, because the N value also reflects how far away these electrons can be from the nucleus, and therefore the size of those orbitals. And so they tend to be the outermost highest energy electrons. So for bromine, the valence level is N equals 4. For oxygen, the valence level is N equals 2 because it has electrons in the N equals 2 level. For lithium, the valence level is N equals 2, and so forth. So that's just a clarification on what valence shell means, or valence level means. It's the highest energy level value, the N value, that has electrons in it. The second thing I would like to talk about is noble gas stability. So we know that noble gases are called noble gases because they don't interact much with the other elements. They're not reactive. And you may recall from your previous chemistry class that the reason that noble gases are not reactive is because they have filled valence levels or valence shells. So what does this mean? Let's take a look back here. This is an electron diagram of bromine. So we have electrons already in it all the way up to the 35 electrons for bromine. But I want to point out that up to this point right here, if we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons, we would have completely filled the N equals 2 valence level. And that completely filled N equals 2 level has a particular stability because it does not need any more electrons to fill its valence level, and it does not want to lose electrons because then it would no longer have that filled valence level. And so just up to this point, this is neon. If we just talked about the N equals 1 valence level, right here, it's helium. So a filled N equals 1 valence level would make that helium. A filled N equals 2 level makes that neon, and so forth. So the reason that noble gases are stable and do not interact or react much with other elements is because they have a filled shell or a filled valence level. And so I just want to make a note here that noble gas stability comes from having filled valence shells. And I just wanted to make those two quick notes so that we don't lose track of them, because that is going to become important as we move on to our next topic and talk about these exceptional cases in electron filling, because those exceptions have a lot to do with stability in the valence shells.